Close your eyes and let yourself drift. Drift down through layers of blue, down past where sunlight dances on waves, down into the quiet darkness of the deep. Tonight, we're descending to the most remote place on Earth, a place deeper than Mount Everest is tall, a place where the weight of the entire ocean presses down with a force that would crush almost anything in an instant. This is the Mariana Trench, and at its deepest point lies the Challenger Deep, nearly 7 miles beneath the surface. 7 miles. If you could somehow stand at the bottom and look up, the surface would be farther away than a cross-country road trip. The pressure here reaches more than 15,000 pounds per square inch, more than 1,000 times the pressure you feel right now, sitting comfortably wherever you are. To understand this place, we must first understand how it came to be. The Mariana Trench sits in the western Pacific Ocean, formed where two massive tectonic plates meet. Here, the Pacific Plate is slowly sliding beneath the smaller Mariana Plate, diving down into the Earth's mantle in a process that has continued for millions of years. This subduction zone created a crescent-shaped scar in the ocean floor, stretching for more than 1,500 miles, longer than the distance from New York to Miami. The trench itself is ancient, formed over 180 million years ago during the Jurassic period, when dinosaurs still walked the Earth. While life above changed dramatically, continents shifted, species rose and fell, ice ages came and went, the Challenger Deep remained, dark and still, 7 miles down. The deepest point was named after the HMS Challenger, the British survey ship that first measured the trench's depths in 1875. Using weighted ropes, the crew recorded a depth of over 26,000 feet. They couldn't have known then just how much deeper it truly went, or that more than a century later, their ship's name would mark the deepest place any human would ever venture. In 1960, two men made history. Jacques Picard and Don Walsh descended in a bathyscaphe called the Trieste, becoming the first humans to reach the bottom of the Challenger Deep. Their journey took nearly 5 hours, slowly sinking through the darkness. At 35,814 feet below the surface, they touched down on a landscape no human eyes had ever seen. They stayed for only 20 minutes before beginning their ascent, but in that brief time, they glimpsed something extraordinary. Even here, in this impossible place, there was life. It would be more than 50 years before another human returned. In 2012, filmmaker James Cameron made a solo dive in his specially designed submersible, the Deep Sea Challenger. Spending 3 hours at the bottom, he captured the first high-definition footage of this alien world. What he found was not a barren wasteland, but a realm of strange beauty, a place where life had adapted in ways that seem almost impossible. The water temperature at the bottom hovers just above freezing, between 34 and 39 degrees Fahrenheit. In this cold, dark, crushing environment, time moves differently. Everything here exists in slow motion, each movement deliberate, each moment stretched thin by the weight of the ocean above. And yet, against all odds, the Challenger Deep is not lifeless. It is home to creatures that have evolved in total isolation, shaped by pressure and darkness into forms unlike anything else on Earth. As we continue our journey tonight, we'll meet these creatures, explore this landscape, and discover how life finds a way, even in the most extreme place our planet has to offer. But for now, just rest, and imagine yourself suspended in that perfect darkness, 7 miles down, where the weight of the world above creates a strange kind of peace. Let your mind drift deeper now, into the landscape of the abyss. If you could somehow see through the darkness, you would find yourself standing on a floor of soft, gray ooze. This sediment, accumulated over millions of years, is made up of the remains of countless microscopic organisms that once lived in the sunlit waters far above. They drifted down like snow, a gentle, eternal snowfall that takes weeks, sometimes months, to complete its journey from surface to seafloor. Scientists call this marine snow, and it falls continuously, building up the ocean floor grain by grain, century by century. The Challenger Deep is not flat. The seafloor here rises and falls in gentle slopes and small valleys, and at certain points, hydrothermal vents pierce through the crust. These vents release water heated by the Earth's interior, sometimes reaching temperatures of 700 degrees Fahrenheit. In this freezing environment, these vents create small oases of warmth, and around them, microbial life thrives in ways that defy everything we once thought we knew about the requirements for life. These microbes don't need sunlight. They feed on chemicals, hydrogen sulfide, methane, transforming poison into energy through a process called chemosynthesis. The creatures that live here have adapted to the pressure in extraordinary ways. Unlike humans, whose bodies contain air pockets that would collapse under such weight, deep-sea organisms have no empty spaces inside them. Their bodies are filled with water and specialized proteins that remain stable under extreme pressure. Some fish here have bodies that are almost gelatinous, with bones that bend rather than break, and cells that function perfectly where ours would be crushed instantly. Among the strangest inhabitants are the amphipods, small, shrimp-like creatures that scavenge the ocean floor. In 2019, scientists discovered amphipods in the Mariana Trench that measured nearly a foot long, giants compared to their shallow water cousins. These pale, ghostly creatures move through the darkness with surprising grace, their bodies containing special fats and organic molecules that help them withstand the pressure. When researchers brought some to the surface for study, they found that these amphipods contained pollutants, PCBs and other toxic chemicals that had somehow made their way from the surface world down to the deepest place on Earth, a sobering reminder that even 7 miles down, nothing is truly untouched by human activity. But life here is not abundant. Food is scarce in the abyss. The marine snow that drifts down provides some nourishment, but it's not enough to support large populations. Scientists estimate that the biomass at the bottom of the Challenger Deep is incredibly low, perhaps thousands of times less than what you'd find in a similar area of shallow coastal water. Every meal is precious. Every calorie must be conserved. The animals here move slowly, deliberately, their metabolisms running at a fraction of the speed of their surface relatives. One of the most remarkable discoveries from the deep is the snailfish. In 2017, researchers captured footage of a ghostly, translucent fish swimming at depths of more than 26,000 feet in the Mariana Trench. The Mariana snailfish, as it came to be called, is unlike any fish that lives in shallower waters. Its body is soft, almost pudding-like, with minimal bone structure. Its skin is nearly transparent, and it lacks scales entirely. This fish represents the deepest living fish ever recorded, existing at depths where scientists once thought vertebrate life was impossible. The darkness here is absolute. No trace of sunlight penetrates this deep, not even the faintest glimmer. The only light comes from bioluminescence, the living light produced by certain organisms. Some deep-sea creatures create their own light through chemical reactions in their bodies, using it to attract prey, communicate with potential mates, or startle predators. In the Challenger Deep, these tiny sparks of light are the only stars in an endless night, brief flashes in the void that reveal, for just a moment, the strange shapes of life adapted to extremes. Time passes differently here. With no day or night, no seasons, no changing light to mark the hours, existence becomes untethered from the rhythms we know. Some fish in the deep sea live for decades, even centuries, their slow metabolisms allowing them to survive for extraordinary spans of time. Growth is slow. Reproduction is slow. Everything is conserved, every process stretched out across years that blend together in the perpetual darkness. And still, we've barely begun to explore this world. Less than 5% of the ocean floor has been mapped in detail, and the deep trenches remain among the least understood places on our planet. Each expedition brings new discoveries, new species, new behaviors, new mysteries. The Challenger Deep holds secrets we haven't yet imagined, life forms we haven't yet encountered, stories written in the sediment and in the genes of creatures who have lived in isolation for millions of years. Rest now, and let yourself float in that quiet darkness, where the only sound is the faint creak of the ocean above, and the only movement is the slow drift of marine snow, falling like stars through an ocean of night. Breathe slowly, and descend with me deeper still into the mysteries of this place. The Challenger Deep is not alone in its extremity. The Mariana Trench is just one of several deep ocean trenches that circle the Pacific Ocean, forming what scientists call the Ring of Fire. But the Challenger Deep holds the record, at approximately 36,000 feet deep, give or take a few dozen feet depending on which survey you consult. It is the deepest point in all of Earth's oceans. To put this in perspective, if you placed Mount Everest at the bottom of the Challenger Deep, its peak would still be more than a mile underwater. The exact depth has been measured multiple times over the decades, and each expedition refines our understanding. Modern sonar technology has mapped the trench with increasing precision, revealing its V-shaped profile. The walls slope down at angles that would make any mountain climber's heart race, dropping thousands of feet within just a few miles of horizontal distance. These slopes are not smooth, they're carved with submarine canyons, scarred by ancient landslides, shaped by forces we're only beginning to understand. The trench sits in the Hadal zone, named after Hades, the ancient Greek underworld. This zone encompasses all ocean depths below 20,000 feet, where pressure exceeds 600 times that of sea level. The Hadal zone represents less than 1% of the ocean floor, found only in these deep trenches. It is Earth's final frontier, more remote, more hostile, more mysterious than the surface of Mars. We have better maps of Mars than we do of the Hadal zone. Within the Challenger Deep, scientists have discovered something unexpected: movement. The water here is not stagnant. Deep ocean currents, driven by differences in temperature and salinity, flow through the trench, carrying nutrients and particles across vast distances. These currents are slow, moving just inches per hour in some places, but they connect the deepest parts of the ocean to the rest of the marine world. Water that sinks into the trench may have begun its journey in the Arctic or Antarctic, taking centuries to complete its circulation through the ocean's depths. The rock that forms the trench is ancient oceanic crust, some of it more than 170 million years old. As the Pacific Plate continues its slow dive beneath the Mariana Plate, it carries with it sediments, minerals, and even water locked within its structure. This water, released as the plate descends into the mantle, plays a crucial role in volcanic activity around the Pacific Ring of Fire. In essence, the Challenger Deep is not just a passive feature, it's an active participant in the geological processes that shape our planet. Among the discoveries made in recent expeditions are anemones, delicate, flower-like creatures clinging to rocks in the deepest parts of the trench. These anemones have tentacles that drift in the gentle currents, waiting to capture any organic matter that drifts within reach. Their presence this deep challenges what we thought we knew about where complex life could survive. They've been found at depths exceeding 34,000 feet, farther down than almost any other complex organism. Scientists have also found evidence of xenophyophores in the Mariana Trench, single-celled organisms that can grow to enormous sizes, some exceeding 4 inches across. These strange creatures are among the largest single-celled organisms on Earth, and they thrive in the soft sediment of the abyss. They build intricate shells from particles they collect, creating delicate structures that look almost artificial, like tiny sculptures made by an invisible artist. Their role in the deep-sea ecosystem is still being studied, but they appear to be important for mixing and aerating the sediment, creating habitats for even smaller organisms. The discovery of plastic waste in the Challenger Deep marked a sobering moment in ocean exploration. In 2019, explorer Victor Vescovo made a record-breaking dive to the deepest point, spending 4 hours at the bottom in his submersible. Among the rock formations and sediment, his cameras captured images of a plastic bag and candy wrappers. Even here, in the most remote place on Earth, human debris has found its way down through 7 miles of water. The ocean, it seems, has no corner too distant to be touched by our presence. Yet despite this contamination, life persists. The organisms of the Challenger Deep continue their slow existence, adapted to conditions that would destroy us in seconds. They remind us that life is not fragile, it is resilient beyond measure, finding ways to exist in places we once thought were lifeless voids. In the cold, the darkness, and the crushing pressure, evolution has crafted solutions we're only beginning to understand. Let your breathing slow, matching the rhythm of those deep currents, moving through the darkness at their own unhurried pace. There is no rush here, no urgency. Only the eternal patience of the deep, where 1,000 years passes like a single breath. As we settle deeper into our journey, let's turn our attention to the remarkable ways life has adapted to exist in this extreme environment. The fish of the Challenger Deep have evolved strategies that seem almost impossible. Many species here have bodies that are more than 90% water, with very little muscle mass and bones that are thin and flexible, almost cartilaginous. This composition allows them to exist in balance with the tremendous pressure. Their internal pressure matches the external pressure, creating a kind of equilibrium that lets them move freely through their world. One of the most fascinating adaptations involves the proteins within these creatures' cells. Under extreme pressure, normal proteins would denature and cease to function, much like an egg white solidifies when heated. But deep-sea organisms produce special proteins, including one called TMAO, trimethylamine N oxide, which acts as a molecular shield. TMAO stabilizes other proteins and prevents them from collapsing under pressure. The deeper an organism lives, the more TMAO it produces. Scientists have found that there appears to be a depth limit to this adaptation, around 27,000 to 28,000 feet, beyond which even TMAO cannot protect cellular function. This may explain why fish are rarely found below this threshold, though other life forms persist even deeper. The eyes of deep-sea creatures tell their own story of adaptation. In the upper reaches of the Hadal zone, some fish have evolved enormous eyes to capture what little bioluminescent light exists. But in the deepest parts of the Challenger Deep, many organisms have lost their eyes entirely. Vision becomes useless in absolute darkness, so evolution has taken a different path. These blind creatures navigate their world through other senses, detecting vibrations in the water, sensing chemical trails, feeling pressure changes with specialized organs along their bodies. They've learned to read the ocean in ways we cannot imagine. The Mariana Trench is not geologically quiet. The subduction process that created it continues today, making this one of the most seismically active regions on Earth. Earthquakes are common here, some measuring above magnitude 7 on the Richter scale. These deep earthquakes occur as the Pacific plate grinds and fractures under tremendous forces, descending into the mantle. The deepest earthquake ever recorded occurred in the Mariana subduction zone at a depth of 460 miles beneath the surface, far below the ocean floor itself, deep within the Earth's mantle where rock behaves almost like a viscous fluid under immense heat and pressure. When these earthquakes occur, they can trigger submarine landslides. Millions of tons of sediment suddenly give way, cascading down the trench walls and underwater avalanches. These events reshape the seafloor, burying whatever lies in their path and creating new terrain. For the creatures of the deep, these landslides are catastrophic events that can wipe out entire populations in moments. Yet life always returns, slowly recolonizing the disturbed areas, carried by currents or drifting down from above. The water in the Challenger Deep contains dissolved oxygen, essential for most complex life. This oxygen originates at the surface, where it's absorbed from the atmosphere. It then travels down through a process called thermohaline circulation, the ocean's great conveyor belt, driven by differences in temperature and salinity. Water that sinks into the deep ocean can take more than 1,000 years to complete its journey through the abyss and back to the surface. The oxygen reaching the Challenger Deep today may have last touched the atmosphere during medieval times, when Vikings sailed the northern seas and the Great Wall of China was being extended. Despite the extreme conditions, scientists have discovered that some bacteria in the Mariana Trench are capable of surviving on hydrocarbons. Essentially, they can feed on oil and natural gas that seeps through the ocean floor. These chemosynthetic bacteria form the base of a food web that exists independently of sunlight. They cluster around cold seeps, areas where methane and other hydrocarbons bubble up from beneath the sediment. Around these seeps, unique ecosystems develop, with worms, crustaceans, and other organisms feeding on the bacteria or on each other in a miniature oasis of life. One of the strangest fish ever filmed in the Hadal zone is the ethereal snailfish, captured on video during a 2014 expedition. This fish appears almost ghost-like, with translucent skin that reveals its internal organs. Its fins are delicate and flowing, giving it an almost angelic appearance as it hovers in the water. The researchers who first saw the footage were struck by how graceful it appeared, how utterly at home in an environment that would be instantly fatal to almost any other vertebrate on Earth. It moves through the darkness with a serene confidence, perfectly adapted to its impossible world. Close your eyes now and picture yourself drifting alongside this ghostly fish, suspended in the quiet darkness. There is no struggle here, no strain. Just existence, pure and simple, in a place where the rules of life have been rewritten. Float here a while, in the peace of the deepest deep, where the weight of the ocean becomes not a burden but a blanket, pressing gently, holding you in perfect stillness. Let us drift now through the layers of time itself, for the Challenger Deep is not just a place, it is a chronicle, a living archive of Earth's history written in sediment and stone. The mud at the bottom accumulates at an extraordinarily slow rate, sometimes just a few millimeters every 1,000 years. This means that if you could dig down through the sediment, you would be traveling backward through time, layer by layer, finding evidence of ancient climates, volcanic eruptions, and even asteroid impacts preserved in microscopic detail. Scientists have taken core samples from the trench floor, extracting cylinders of sediment that reveal secrets spanning millions of years. Within these cores, they've found ash layers from volcanic eruptions that occurred when mammoths still walked the Earth, and traces of cosmic dust from meteor showers that lit up prehistoric skies. Each layer is a page in Earth's storybook, and the Challenger Deep holds chapters that exist nowhere else, protected from the erosion and disturbances that affect shallower waters. The salinity of the water in the deepest parts of the trench is remarkably consistent, about 34.7 parts per thousand, just slightly higher than average ocean water. This consistency is maintained by the great ocean currents that flow through the Hadal zone, mixing water masses and preventing the formation of extreme chemical gradients. Yet even tiny variations in salinity can affect how sound travels through water, and researchers have used these variations to map currents and water movements that would otherwise remain invisible. Sound behaves strangely in the deep ocean. At certain depths, around 3,000 feet down, there exists a layer called the SOFAR channel, the sound fixing and ranging channel, where sound waves can travel for thousands of miles with minimal loss of energy. This occurs because of the way temperature and pressure affect the speed of sound in water. While the Challenger Deep sits well below this channel, the sounds generated there, the clicks and calls of animals, the rumble of earthquakes, the crack of shifting ice from polar regions, can travel up into the so far channel and propagate across entire ocean basins. In this way, the deep is not silent but connected, part of a vast acoustic network that spans the globe. Among the most enigmatic inhabitants of the Hadal zone are the sea cucumbers. These soft-bodied creatures drift across the seafloor on small tube feet, vacuum feeding on organic particles in the sediment. In the Challenger Deep, researchers have observed sea cucumbers in shades of pale pink and translucent white, some measuring more than a foot long. They move with glacial slowness, processing sediment and extracting every possible nutrient. One study estimated that a single sea cucumber might consume and process several pounds of sediment each year, playing a crucial role in recycling nutrients in this food-scarce environment. The oldest living organisms in the Hadal zone may be the deep-sea corals and sponges that attach to rocky outcrops. While most people think of coral as tropical reef builders, certain coral species thrive in the cold, dark waters of the deep ocean. These corals grow incredibly slowly, some adding less than a millimeter of skeleton per year. Radiocarbon dating of deep-sea corals has revealed individuals that are thousands of years old, making them among the oldest living animals on Earth. They were alive when the pyramids were built, when Rome rose and fell, when the New World was discovered. They've witnessed the entire span of human civilization from their perch in the abyss. The Mariana Trench experiences tidal forces just like the rest of the ocean, though the effects are subtle at such depths. Twice daily, as the moon pulls on Earth's waters, the pressure at the bottom of the trench fluctuates slightly, by about 2 to 3%. This may seem insignificant, but for organisms living at the edge of what's physically possible, even these small variations in pressure can influence behavior. Some scientists theorize that deep-sea creatures may time their activities to these tidal cycles, though proving this in such a remote and difficult-to-study environment remains a challenge. In 2009, researchers using advanced sonar systems discovered mud volcanoes in the Mariana Trench. These formations occur when pressurized mud and water from deep beneath the seafloor find weak points in the crust and erupt upward, creating cone-shaped mounds on the ocean floor. Some of these mud volcanoes rise hundreds of feet above the surrounding seafloor. The mud they expel is often warm and rich in minerals, and around them, unique microbial communities flourish, feeding on the chemicals released from Earth's interior. These mud volcanoes are like windows into the planet's deep geology, offering glimpses of processes occurring miles beneath the surface. Breathe deeply now, and let yourself settle like sediment drifting down through those 7 miles of water. There's no need to hurry. Time moves differently here, measured not in seconds or minutes but in millennia, in the slow accumulation of mud, in the gradual growth of ancient corals. Rest here in this timeless place, where the past and present blur together in the eternal darkness. As we continue our gentle descent through the mysteries of the abyss, let's consider the remarkable chemistry of this place. The water at the bottom of the Challenger Deep is slightly more acidic than surface water, with a pH around 7.7 to 7.9, compared to the surface ocean's 8.1 to 8.2. This increased acidity comes from the enormous pressure forcing carbon dioxide to dissolve more readily into the water, and from the breakdown of organic matter on the seafloor. Yet even with this acidity, the chemistry remains stable enough to support life, a delicate balance maintained over geological timescales. The minerals dissolved in the deep water tell stories of their own. Silica, iron, manganese, and other elements leach slowly from the volcanic rock of the trench walls and from the sediment itself. These minerals accumulate in nodules, potato-sized rocks that grow on the seafloor over millions of years, accreting layer upon layer like underwater pearls. Some of these polymetallic nodules are incredibly old, containing rare earth elements that have made them targets for future deep-sea mining operations, though the environmental consequences of such mining in these pristine environments remain hotly debated. The creatures of the Challenger Deep have evolved unique reproductive strategies suited to their sparse, challenging world. Many deep-sea fish are hermaphroditic, possessing both male and female reproductive organs, which increases their chances of successful reproduction when encountering another member of their species as a rare event. Some species have males that are much smaller than females, and certain anglerfish species from related deep zones, the tiny male actually fuses permanently to the female's body, becoming little more than a sperm-producing appendage. In the vast emptiness of the Hadal zone, finding a mate is such a challenge that evolution has created solutions that seem almost alien. Reproduction itself happens slowly in the deep. Many organisms produce very few offspring, investing heavily in each one. Eggs may be unusually large, packed with nutrients to give the developing embryo the best chance of survival. Development can take months or even years in the cold water where metabolic processes crawl along at a fraction of surface speeds. A creature that reproduces once in its lifetime, after decades of slow growth, represents an enormous investment of time and energy, and the loss of even a few individuals can impact populations for generations. The Japanese crewed submersible Shinkai 6500 has made numerous dives to explore the Hadal zone, though it can only reach depths of about 21,000 feet, less than two-thirds of the way to the Challenger Deep's bottom. This vessel has nonetheless made remarkable discoveries, documenting species and geological features throughout the deeper parts of the ocean. Each dive by Shinkai or other submersibles represents years of planning, millions of dollars in costs, and tremendous risk. The technology required to withstand Hadal pressures is at the very edge of human engineering capability, with viewing ports made of acrylic or glass that must be perfectly manufactured to avoid catastrophic failure. Temperature inversions occasionally occur in the trench, where pockets of slightly warmer water become trapped beneath colder layers due to subtle differences in salinity and density. These inversions can create microenvironments within the larger trench system, potentially harboring unique communities of organisms adapted to these specific conditions. Scientists have only recently begun to understand how these thermal layers interact and how they might influence the distribution of life in the Hadal zone. Among the most recently discovered features of the Mariana Trench are brine pools, small lakes of extremely salty water that form on the seafloor. These pools are denser than the surrounding seawater and remain separate, creating what looks like an underwater lake complete with a distinct shoreline. The brine in these pools can be several times salter than normal seawater and is often toxic to most forms of life, yet specialized bacteria thrive along the edges, and occasionally, an unlucky creature that wanders into the brine becomes preserved, creating an eerie underwater graveyard. The Mariana Trench lies entirely within the exclusive economic zone of the United States, as it falls near the U.S. territories of Guam and the Northern Mariana Islands. This means the United States technically has jurisdiction over this deepest point on Earth, though international scientific cooperation remains the norm for research expeditions. The geopolitical significance of the trench extends beyond science. It represents strategic territory in an increasingly important region of the Pacific, and its remoteness and depth make it a subject of military interest as well. Let your mind rest now in these deep brine pools, in these quiet pockets where water within water creates boundaries we can barely perceive. Everything here exists in layers, layers of water, layers of sediment, layers of time stretching back to when the world was young. Settle into these layers, let them hold you gently, and feel the slow pulse of a world that exists beyond time, beyond light, beyond everything you know. Now, let us explore the very frontier of what we know, the edge of understanding where science meets mystery. The deepest parts of the Challenger Deep remain largely unexplored. Fewer than a dozen people have ever visited the bottom, and the total time humans have spent there amounts to less than a single day. Compare this to the International Space Station, which has been continuously occupied for over 2 decades, and you begin to understand just how remote this place truly is. We know more about the surface of Mars than we do about the deepest trenches of our own planet. The pressure differential between the surface and the Challenger Deep creates interesting effects on equipment. When submersibles descend, their hulls compress slightly under the increasing pressure. Titanium spheres that house the crew can shrink by nearly an inch in diameter at maximum depth. This compression is reversible, and as the vessel ascends, it expands back to its original size. But this constant squeezing and releasing, dive after dive, creates mental fatigue that limits how many times a submersible can safely make the journey. Each dive literally takes years off the vehicle's operational life. The food web in the Challenger Deep is fundamentally different from what we see in shallower waters. With no photosynthesis possible in the eternal darkness, every calorie must either drift down from above as marine snow or be produced by chemosynthetic bacteria. This makes the Hadal zone one of the most energy-poor environments on Earth. Creatures here have evolved to survive on remarkably little food. Their metabolic rates are so slow that some fish may need to eat only a few times per year. A single fallen whale carcass reaching the trench floor represents a bonanza of nutrition that can sustain an entire community for decades. Indeed, whale falls are rare but crucial events in the deep ocean. When a whale dies and sinks, it brings with it tons of organic matter, blubber, muscle, bone, all rich in fats and nutrients. Within hours of reaching the seafloor, scavengers begin to gather. Hagfish, amphipods, and other creatures swarm over the carcass, consuming the soft tissue. This initial scavenging stage can last months. Then comes the enrichment stage, where the fats and oils that have seeped into the surrounding sediment support dense bacterial mats and worms for years. Finally, the sulfophilic stage begins, as bacteria colonize the bones themselves, breaking down the fats within and creating a chemosynthetic community that can persist for 50 years or more. A single whale fall becomes an oasis, an island of abundance in a desert of sediment. The rocks at the bottom of the Challenger Deep are primarily basalt and peridotite, volcanic rocks from the Earth's mantle and oceanic crust. Some of these rocks show signs of serpentinization, a chemical process where minerals react with seawater to produce hydrogen gas and heat. This process not only generates energy that can support microbial life but may have played a crucial role in the origin of life itself billions of years ago. The Challenger Deep, in this sense, is not just a place to study how life survives extreme conditions, it may hold clues to how life began. The biomass of bacteria in the sediment of the Challenger Deep is surprisingly high compared to the larger organisms swimming in the water column above. These microbes exist in the mud, sometimes buried meters deep, living off the slow trickle of organic matter and the chemicals released by geological processes. They divide perhaps once every few years, existing in a state that seems almost suspended between life and dormancy. Recent studies suggest that the total microbial biomass in deep ocean sediments may rival that of all the ocean's surface waters combined, a hidden biosphere we're only beginning to appreciate. Water clarity in the Challenger Deep is exceptionally high. With no sediment being stirred up by storms, no algae blooms, and minimal organic particulates, the water is remarkably transparent, if you could somehow see in total darkness. Measurements suggest that if you could shine a light, you might be able to see clearly for more than 300 feet in any direction, farther than in most coastal waters. This clarity means that any bioluminescent flash can be seen from great distances, making light an efficient form of communication in the void. The total volume of water in the Mariana Trench is estimated at around 2,500 cubic miles, a vast reservoir of cold, dense water that plays an important role in global ocean circulation. This water is among the densest in the world ocean, and as it slowly flows out of the trench and spreads across the Pacific Basin, it forms the bottom layer of the deep ocean, influencing water properties across thousands of miles. The Challenger Deep, then, is not isolated but intimately connected to the entire planetary ocean system. Rest now in this clarity, this perfect transparency that exists unseen in the darkness. Imagine yourself suspended in water so pure, so still, that you could see for hundreds of feet if only there were light. But there is no light, and in this absence, there is a different kind of seeing, a sense of space and depth and presence that requires no eyes. Float here, in this pure water, this quiet space, and let the darkness become not an absence but a presence of its own, gentle and complete. Let us turn our thoughts now to the delicate balance of this ecosystem, to the intricate relationships that connect predator and prey, scavenger and bacteria, in a world where every interaction happens in slow motion. The copepods of the Hadal zone, tiny crustaceans smaller than a grain of rice, have been found at depths exceeding 35,000 feet. These microscopic creatures drift through the water column, feeding on even smaller particles in bacteria. Despite their size, they play an outsized role in the food web, serving as prey for larger organisms and helping to break down organic matter into forms that bacteria can process. Their bodies are adapted to withstand pressure that would instantly destroy their shallow water cousins, yet under a microscope, they appear almost unchanged, a testament to the conservative nature of evolution when a design works perfectly. The gradient of pressure from the surface to the Challenger Deep creates distinct zones of life, each with its characteristic inhabitants. Between 20,000 and 26,000 feet lies a transitional zone where fish become increasingly rare and invertebrates begin to dominate. Below 26,000 feet, fish virtually disappear, and the ecosystem is ruled by amphipods, sea cucumbers, and microscopic organisms. This boundary appears to be absolute, a line drawn by the limits of biochemistry itself, where the pressure becomes too great for even the most specialized fish to maintain their cellular integrity. The Mariana Trench experiences virtually no seasonal variation. While surface waters shift dramatically with the changing sun, warming in summer, cooling in winter, blooming with life in spring, the Hadal zone remains constant. The temperature hovers around 1 to 4 degrees Celsius year-round, the pressure never wavers, and the darkness is eternal. For organisms here, there is no spring awakening, no autumn decline. Life proceeds at the same measured pace century after century, unchanging, unaffected by the cycles that govern the rest of the planet. Among the strangest findings from deep-sea expeditions are soft-bodied organisms that seem to have no hard parts whatsoever, no shells, no bones, no protective armor. These creatures, which include certain types of jellyfish and comb jellies, drift through the Hadal zone like ghosts. Their bodies are more than 95% water, making them nearly neutrally buoyant and requiring minimal energy to move. When preserved for study, they often collapse into shapeless blobs, losing all the delicate structure they possessed in life. This is why many deep-sea species have been observed by cameras but never successfully brought to the surface intact. The Challenger Deep sits at the boundary between two of Earth's largest tectonic plates, and the forces involved are almost incomprehensible. The Pacific Plate is being pushed downward at a rate of about 2 to 3 inches per year, roughly the same rate your fingernails grow. This seems incredibly slow, but over millions of years, this movement has carried ancient seafloor hundreds of miles down into the mantle. The rocks at the bottom of the trench are transitioning from one state to another, from the rigid crust we know at the surface to the ductile, flowing rock of the mantle below. In a sense, the Challenger Deep is a gateway between worlds, between the solid Earth we inhabit and the viscous, semi-molten interior. Scientists have detected trace amounts of radioactive materials in the sediments of the Mariana Trench, not from natural sources, but from nuclear weapons testing conducted in the atmosphere during the 1950s and 1960s. These radioactive particles fell onto the ocean surface decades ago, then slowly made their way down through the water column, eventually settling into the deepest sediments on Earth. They serve as time markers, allowing researchers to measure sedimentation rates and trace the movement of particles through the ocean. Even here, 7 miles from the surface world, we find evidence of humanity's brief but intense flirtation with atomic power. The discovery of active microbial communities living within the rock itself, in tiny pore spaces and fractures in the basalt of the trench walls, has expanded our understanding of where life can exist. These endolithic microbes, living within stone, survive on chemical energy derived from reactions between rock and water. They grow incredibly slowly, perhaps dividing once every few hundred years, existing in a state that barely qualifies as life by our usual definitions. Yet they persist, representing a form of existence that may be common throughout Earth's crust and perhaps throughout the universe wherever liquid water contacts rock. The amount of pressure acting on each square inch of surface at the Challenger Deep is roughly equivalent to having 50 jumbo jets stacked on top of your thumb. For perspective, a human body at the surface experiences about 14.7 pounds per square inch of atmospheric pressure. At the bottom of the Challenger Deep, that figure rises to more than 16,000 pounds per square inch. If an unprotected human body were somehow transported instantly to that depth, it would not be crushed in the dramatic way often portrayed in films. Instead, the air spaces would collapse immediately, including the lungs and sinuses, while the water-filled tissues would remain relatively intact, though death would be instantaneous. Close your eyes and breathe slowly, feeling the gentle weight of air pressing against your skin, a whisper compared to the tremendous force at the bottom of the ocean. Yet even there, life persists, adapted, balanced, at peace with forces we can barely imagine. Let yourself sink deeper into rest, deeper into this story of extremes, where life has found not just survival but a kind of harsh perfection. As we near the completion of our journey through the Challenger Deep, let us contemplate the lessons this place teaches us about resilience, about patience, about the fundamental nature of life itself. The deep ocean is often called the largest habitat on Earth, and this is not an exaggeration. The Hadal zones of all the world's trenches combined cover an area roughly the size of Australia, yet they remain among the least explored regions of our planet. The Challenger Deep represents the very deepest part of this vast realm, the ultimate expression of what the ocean can be. The chemistry of life itself functions differently under such extreme pressure. Enzymes, the molecular machines that drive all biological processes, must be specially adapted to maintain their shape and function when compressed by thousands of pounds per square inch. Researchers studying Hadal organisms have discovered that their enzymes contain unusual amino acid sequences that make them naturally pressure-resistant. Some of these enzymes actually work better under high pressure than they do at the surface, falling apart or becoming sluggish when the pressure is released. These organisms are not just tolerant of the deep, they are dependent on it, unable to survive in the shallower waters that seem so hospitable to us. The isolation of the Mariana Trench has led to the evolution of endemic species, creatures found nowhere else on Earth. Because the Hadal zones are separated from each other by thousands of miles of shallower seafloor, organisms in one trench cannot easily reach another. Each trench becomes its own evolutionary laboratory, where species diverge and adapt to local conditions over millions of years. The amphipods of the Mariana Trench are genetically distinct from those in the Tonga Trench or the Chromatic Trench, despite their similar appearances. They are cousins separated by geography and time, each population telling its own evolutionary story. Sound travels faster in the Challenger Deep than it does at the surface, reaching speeds of about 5,300 feet per second compared to roughly 4,900 feet per second in surface waters. This is because the extreme pressure increases the density of water, allowing sound waves to propagate more efficiently. For organisms that use sound to navigate or communicate, if any exist at these depths, this would create an acoustic environment quite different from anything in shallower waters. However, we still know very little about whether Hadal organisms produce or perceive sound at all. The Mariana Trench contains pockets of altered seawater chemistry where hydrothermal activity has been active in the past. These fossil hydrothermal systems, now dormant, left behind mineral deposits rich in metals like copper, zinc, and gold. These deposits represent concentrated ore bodies formed by the same processes that create valuable mineral deposits on land. While they remain untouched for now, protected by their remoteness and the extreme difficulty of mining at such depths, they represent resources that future generations may seek to exploit, raising complex questions about how we balance scientific preservation with economic development. The deepest diving marine mammal ever recorded is the Cuvier's beaked whale, which has been documented reaching depths of nearly 10,000 feet and holding its breath for over 2 hours. While this is nowhere near the Challenger Deep, it represents the absolute limit of where warm-blooded, air-breathing vertebrates can venture. The physiological adaptations required for these whales to reach even this depth, collapsible lungs, oxygen stored in muscles rather than lungs, slowed heart rate, are extraordinary. The gulf between what a whale can achieve and what would be required to reach the Challenger Deep illustrates just how alien the Hadal zone truly is. Recent studies have revealed that amphipods from the Mariana Trench contain high levels of aluminum in their bodies, far higher than would be expected from natural sources. The origin of this aluminum remains uncertain, but it may come from the breakdown of terrestrial materials, dust, sediments, that have made their way into the ocean over millennia. This finding highlights how even the deepest parts of the ocean are connected to terrestrial processes, receiving inputs from continents thousands of miles away through atmospheric transport and ocean currents. The future of Challenger Deep exploration likely lies not with human-occupied submersibles but with autonomous underwater vehicles, robots that can explore for extended periods without the weight and life support systems required for human passengers. Several such vehicles are in development, equipped with advanced cameras, sampling equipment, and artificial intelligence that allows them to make decisions independently. These robotic explorers could map the trench in unprecedented detail, collect samples from dozens of locations, and perhaps even discover entirely new ecosystems. The age of remote exploration is just beginning, and what we learn in the coming decades may revolutionize our understanding of the deep ocean. Breathe now, slowly and deeply, and imagine the future, a time when the mysteries of the Challenger Deep are finally revealed, when we understand the full catalog of life in the Hadal zone, when the last blank spaces on Earth's map are finally filled in. But for now, in this moment, the deep remains mostly unknown, mostly unexplored, a frontier that still holds countless secrets. And there is something beautiful in that, something worth preserving, the knowledge that our world still contains places beyond our reach, depths we have barely begun to fathom. Rest in that mystery, that unknowing, that vast and patient darkness. And so we arrive at the end of our journey, having traveled through 7 miles of ocean, through layers of time and pressure and life that defies expectation. Let us gather the final threads of this story, the last facts that complete our understanding of this remarkable place. The energy budget of the Challenger Deep is extraordinarily low. Scientists estimate that the total amount of organic carbon reaching the deepest parts of the trench might be less than 1 gram per square meter per year, roughly the weight of a paperclip spread across an area the size of a computer screen. Yet from this meager input, entire ecosystems persist, proving that life requires not abundance but merely sufficiency. The organisms here have mastered the art of making do with almost nothing, extracting every possible calorie from every particle that drifts within reach. The water column above the Challenger Deep serves as a natural laboratory for studying how particles fall through the ocean. Researchers have deployed sediment traps at various depths to measure the rate at which organic matter sinks. They've discovered that the journey from surface to seafloor is not a steady drift but a complex process involving biological transformation, aggregation, and disaggregation. Particles may be consumed and excreted multiple times by different organisms during their descent, each interaction changing their composition and density. By the time organic matter reaches the Hadal zone, it has been processed so thoroughly that little of its original structure remains. Among the most peculiar residents of the trench are the foraminifera, single-celled organisms that build elaborate shells from calcium carbonate or by cementing together particles of sediment. Some species of foraminifera have been found at the deepest parts of the Challenger Deep, their delicate shells somehow resisting the pressure that would seem capable of crushing them. Under a microscope, these shells reveal chambers and passages, spiral designs and geometric patterns that seem too intricate to be the work of a single-celled organism. Yet they are, representing a form of architectural sophistication that evolved hundreds of millions of years ago and persists unchanged in the abyss. The biological productivity of the Challenger Deep, measured in terms of carbon fixed by chemosynthetic bacteria, is estimated to be less than 0.1% of the productivity in sunlit surface waters. And yet, this tiny trickle of energy supports a complete food web with multiple trophic levels: bacteria, grazers, predators, and scavengers. It demonstrates that ecosystems can function on energy inputs far smaller than we once believed possible, a finding with implications for the search for life on other worlds where energy may be even more scarce. The Mariana Trench continues to reveal surprises with each expedition. In 2020, scientists discovered microplastics in the digestive systems of amphipods from the Challenger Deep, tiny fibers and fragments of plastic that had somehow made the 7-mile journey from the surface. These plastics may have been ingested directly as the amphipods fed on marine snow, or they may have accumulated through the food chain. Either way, their presence serves as a stark reminder that human influence now extends to the furthest reaches of the planet, that there is no place so remote it remains untouched. The total number of known species from the Hadal zone is still remarkably small, perhaps a few hundred have been formally described, though genetic studies suggest thousands more await discovery. Each expedition brings back specimens that represent new species, new genera, sometimes new families of organisms. The rate of discovery suggests that our catalog of Hadal biodiversity is still in its infancy, that we have sampled only a tiny fraction of what exists in these trenches. The Challenger Deep alone may harbor hundreds of species that exist nowhere else on Earth, living out their lives in absolute darkness, unknown and undiscovered. The Philippine Sea Plate, which borders the Mariana Trench to the east, is one of the oldest pieces of oceanic crust on Earth, dating back over 150 million years. As this ancient seafloor is slowly consumed in the subduction zone, it carries with it a record of Earth's history, sediments deposited during the age of dinosaurs, chemical signatures of ancient ocean conditions, perhaps even microbes that have been buried in the crust for geological ages. When the plate finally melts in the mantle, these records will be erased, recycled into new crust that will one day emerge at mid-ocean ridges thousands of miles away. The trench is not just a place, it is a process, a recycling center for the planet's crust. And finally, perhaps the most important fact of all, the Challenger Deep reminds us of how much we have yet to learn about our own planet. In an age where it sometimes seems that everything has been discovered, mapped, and photographed, the Hadal zones stand as monuments to humility. They remind us that Earth is still wild, still mysterious, still capable of surprising us. They challenge us to look deeper, to question our assumptions, to recognize that the universe's greatest mysteries may lie not in distant galaxies but in the depths of our own world's oceans. Let yourself rest now, completely and fully, as if you were settling into the soft sediment at the bottom of the Challenger Deep. 7 miles of water above you, insulating you from the world, the weight of the ocean holding you in perfect stillness. Here, in this imagined darkness, there is no past and no future, only the eternal present of the deep. The pressure that once seemed crushing now feels like an embrace, and the darkness that seemed frightening now feels like peace. Sleep now, and let yourself drift in these depths, knowing that somewhere, 7 miles beneath the waves, the Challenger Deep continues its patient existence, unchanging, mysterious, alive with creatures that have never known light, that move through their world with ancient grace, that carry within them secrets we have barely begun to uncover. Rest in that knowledge. Rest in that mystery. Rest in the deep, dark peace of the ocean's final frontier. And sleep, sleep, sleep.